So to start with, we're asked to find integers m and n such that this is true. By the way, if this is true, then it must also be that this is true. We can square both sides. And in fact, that's going to be my first method I'm going to show you for dealing with this. We could just try some numbers out. The left-hand side is quite small, so m and n are probably going to be quite small. And if we just try 1 and 1, so 1 plus root 2 all squared, then it actually works out. We get 1 plus 2 root 2 plus 2. We get 3, yeah, 3 plus 2 root 2. Okay, that is, nothing wrong with that method whatsoever. So m plus n root 2 is going to be 1 plus root 2. Here's a much longer way to do it. It uses the same sort of ideas, but this time it will work well as well for much larger numbers. 3 plus 2 root 2 is then going to equal m plus n root 2 squared. So this time I'm not trying numbers out. I've got an equation, and I'm going to work out. I'll be able to work out what m and n is. So I've squared both sides. That's much easier to deal with. The right hand side then becomes m squared plus 2n squared plus 2m n root 2. And I can compare coefficients. It must be that 3 is equal to this integer part here. M squared plus 2n squared is 3. And then the third part, or at least the coefficients of the third part, must be equal. So 2 is equal to 2mn, or mn is equal to 1, or n is equal to 1 over m. Brilliant. Now I can substitute that in. So m squared plus 2 over m squared is equal to 3. And you can see this is much more complicated, but it's a nice algebraic method that will work. We can multiply through by m squared, so m to the 4 minus 3m squared plus 2 is equal to 0. I've just times by m squared and rearranged. We have a hidden quadratic in m squared. Let's try and factorize it. Get minus 1 minus 2, that checks out, equals 0. So m squared is 1 or 2, which means m is plus or minus 1 or plus or minus 2. Root 2, I should say. 4 solutions to this. However, we can state that we just want m to be integers. It doesn't, oh yeah, it does even say that at the start. If you wanted to deal with m being a root 2, then you'd get n as third as well, and you'd actually get the same solution. It would work out, but we can just reject it here. And then because we're taking the square root of a positive number, we're going to get a positive number, so we can reject the minus 1. Whatever our answer is, if we took the negative of it, if you squared it, you would get the same thing, 3 plus 2 root 2, but you can see from the question that we're only interested in the positive root. So m is equal to 1, n is equal to 1, and therefore we're going to have 1 plus root 2 just like before. All right, now on to the next bit of the question. So let's just bear that last bit in mind. It's probably going to come back in later on. But actually, now we have a quartic equation. There's no cubic term. Note that. So in fact, the quartic does have a general solution, like really, really long. You could look it up. But it turns out that if you have 4 real roots, I think this is only going to apply because of that, and no cubic term, we can actually solve any quartic that we want using the method we're about to derive. So it's pretty cool. We're asked to explain why f of x can be written as the product of two quadratics to start with. So let's take a look at that. F of x has 4 real roots, so can be written as f of x equals x plus a, x plus b, so the 4 brackets, because that would give us minus a, minus b, minus c, and minus d. And I'm going to remember in the answer, I've got quadratics. I'm going to expand the first 2 out and the second, the third and the fourth out. So I'll get x squared plus a plus b x plus ab. Then similarly x squared plus c plus d x plus cd. So no x cubed term in f of x. So let's work out the x cubed term in terms of a, b, c, d and see what happens. We're going to get one by doing x squared times c plus dx. So the coefficient would be c plus d. And then by doing a plus b x times x squared, which will give us a plus b. So it must be when we add these together, we get 0. And therefore, a plus b is equal to minus c plus d. And you can see we're on our way. I mean, that's why I did it, because look, I've got an s here and a minus s here. So I'm going to call well, you do that a little bit better than that. So s is going to be defined as a plus b. So that means minus s is c plus d. And then my final answer, I've got a p, so I'm going to also define p as a times b. And q is going to be defined as cd. Therefore, f of x equals x squared plus sx. I've just replaced a plus b by s, plus p, which is I know is ab, but we're ignoring that now. And then x squared minus sx, because that's my c plus d, which we've said is minus s, plus q. And we have shown the result. Right, more to do now. We're asked to basically to derive an equation in terms of s. So we've got f of x as two quadratics factorized with s and p there. So we're going to be having p, we're going to try and be eliminating those. And don't forget, we've got our actual quadratic in this case. So I'm just going to bring that down and we're going to compare some more coefficients. So we've got both of these. All right, now no point in comparing the x to the 4 coefficients, they're just both 1. Let's go actually from x to the 0. The only way I'm going to get a constant term from expanding my brackets is p times q. So pq must equal minus 2. Then let's look at the x to the 1 term. I could do sx times q, so my coefficient would be sq, or I could do p times minus s, so that would be sp, and that must equal 12. So I'll leave that like it is for the moment. We've already dealt with x cubed, but not x squared yet. So for x squared, I could do x squared times q, so that would give me q. I could do p times x squared, that would give me p. And there's another one, I could do sx times minus sx, which gives me minus s squared. So those three together must equal minus 10. So we want to combine these three equations to get an equation just in terms of s. Let's use a result to guide us rather than just blindly going into this, because they're quite complicated. We've got a p times a q for a start. The first thing I see is s squared minus 10 in my answer. So if I take this one and add s squared to both sides, I would have s squared minus 10 equals q plus p. And then I can see in the answer I've squared it. So if I square it, I'll have q plus p all squared. Let's just expand that for a minute. I'll get q squared plus p squared plus 2pq. I can start to see how this might be useful because I've got a pq here, so I can replace that in a minute. Let's look at the second one. So if I factorize out the s, I'll have s times q minus p, and that's going to equal 12. And I could then make q minus p the subject. Because if I square that, q minus p squared, I'll have 144 over s squared, but I'll also have something very similar to q plus p squared. I'll have q squared plus p squared, but minus 2qp. And here's what we're left with actually. We've got that q plus p squared. If I minus q minus p squared from it, then I'll have q squared plus p squared plus 2pq minus q squared plus p squared minus 2pq. Everything's gonna cancel out, except I'll be left with 4pq. So I need to minus 4pq, and then I'll get 0. So that is something you need to realize in this question, or at least I feel like this is the quickest route. If you look at the answers, there's another way to do it, but I'm just going to stick with this one. I think it's the best one. Okay, so therefore we can now replace q plus p squared by s squared minus 10 all squared. I can replace q minus p all squared by 144 over s squared. And I can replace 4pq by 4 times minus 2. And that's going to equal 0. I'm going to multiply, look, I'm very close now. You can see I'm going to multiply through by s squared. So s squared times s squared minus 10 squared. And then it's going to be plus 8 s squared, because this is going to become plus 8 here, and then I'm timesing it by s squared, minus 144 is equal to 0. Okay, that is probably the hardest part of this question. And yeah, you might not get it straight away, you might play around with it, go down the wrong path. But I think that my guidance would be look at the final answer, just we've got that. How are we going to get an s squared there? How are we going to use q plus p all squared? And then, it's not obvious, but this is what you have to come up with. Right, we're actually still on this part of the question because we're asked to find the 3 possible values of s squared. Got to solve this now. It's actually going to be s to the power of 6 ultimately. So I'm going to let u equal s squared. Let's do a substitution. Okay, I'm not going to work in terms of s squared. I think that's just going to be complicated. So u times u minus 10 squared plus 8u minus 144 is equal to 0. This is going to become a cubic now, but we can solve cubics. Try use the factor theorem. So u times u squared minus 20u plus 100 plus this is going to equal 0, which means u cubed minus 20u squared. And then I've got 100u plus 8u, so 108u minus 144 is equal to 0. Let's let this thing here be defined as, I don't want to use f, I've already got that, as g of u. And then I'll put some numbers in to see if we can get 0 from it. So g of 1, I always say like to start with. That's clearly not going to work out though. That's not going to be 0. You could go with minus 1 or maybe 2 is the next one. So g of 2 is going to be 8 minus 20 times 4, that's 80, plus 108 times 2, that's 216, minus 144. That'll give me 224 by doing 8 plus 216 minus 224 is equal to 0. This is great. So u minus 2 is a factor by factor theorem. Okay, there's different ways to then factorize it. You could, just do like a trial process, but I always like polynomial division. It doesn't take too long. It's quite a safe way as well. Just remind ourselves, were we trying to find s squared? Okay, so that is one of our solutions for s squared too. Okay, u's into u cubed. go u squared times back through. So I'm at the point where I've written so much that everything starts slowing down on my computer. Minus 18 u squared plus 108. So I'm going to get minus 18u here plus 36. Minus them to give 72. This is looking good. So plus 72 and minus 144. So therefore, u minus 2 multiplied by u squared minus 18u plus 72 is going to equal 0. And the other factors were 6 and 12. Sorry, the other numbers I could have put in, like the solutions are going to be 6 and 12. So u minus 6, u minus 12 equals 0. It's going to go straight for it. S squared is 2, 6, or 12. Nice. We've made it to the final part. We're asked to use the smallest of these values of s squared to solve completely the equation f of x equals 0, simplifying our answers as far as we can. I did ponder after doing this question why we have to use the smallest, and I think the answer is we don't have to use the smallest. I think the 2, 6, and the 12 will give us actually the same solutions. We'll just get slightly different values of p and q depending on what s we choose. So we might as well just choose 2, for example, as the smallest. S squared equals 2. S is equal to plus or minus the square root of 2. But remember, we've got a minus and a plus in our answer. So without loss of generality, we can just say I'm going to take positive. Let me just clarify that a little bit further. Because remember, we had this thing here. So I'll just get, if I take the minus, I could just swap them around. Like it just doesn't matter. So I need to return to here, actually. Right, so I can use, what color shall I use here? So it must be that q plus p minus 2 is equal to minus 10. So q plus p is equal to minus 8. That's one result we get. I'm just going to put a box around it because there's so many different results going on here now. I'm going to ignore the one where we're multiplying p and q and instead return to, I think it was q minus p is 12 over s. So in our case, it's going to be 12 over root 2 or 6 root 2 by rationalizing the denominator times top and bottom by root 2. 12 root 2 over 2 is 6 root 2. I have simultaneous equations in terms of p and q. Let's first of all add them together. So 2q is going to equal 6 root 2 minus 8. So q is going to be 3 root 2 minus 4. I could sub it back in, but I think it's going to be easier to subtract them instead. So 2p, if I take the bottom one and minus the top one, is going to be minus 8 minus 6 root 2. So p is minus 4 minus 3 root 2. And therefore, x squared plus root 2x, that was my s, plus p, so I can do minus 4 plus 3 root 2 here. Then x squared minus root 2x, that's my minus sx, plus q, plus 3 root 2 minus 4. That is equal to 0. And we have factorized that quartic expression. Let's take each one in turn, the left-hand bracket, the right-hand bracket, and solve them. So it's going to be all about the quadratic formula here. Minus b plus or minus b squared minus 4ac. This will become a plus, square rooted all over 2. Over here, I'm going to get 16 plus 2, so 18 plus 12. What can I do? I can't take a nice square number out of this. There's no common, I mean, I can take 9 out of the 18 and 4 out of the 12, but I've got to take it out of both. Let's just return to here though. Remember, right at the start, we had that the square root of 3 plus 2 root 2 was 1 plus root 2. So can we get that? And the answer is yes. If we take out a root 6, then we get the square root of 3 plus 2 root 2 here. So this becomes minus root 2 plus or minus root 6 times 1 plus root 2 all over 2. Which finally is going to give minus root 2. Let's deal with the plus first of all. Plus root 6 plus root 12 all over 2. Or minus root 2 minus root 6 minus root 12 all over 2. Those are two of our solutions. Nicely done. That just leaves us the other quadratic on the right. And it's going to be the same process. I'm going to be adding 16 on again. So again, it's going to be 18, but this time it's minus 12 root 2. Take out that root 6 again. We're left with 3 minus 2 root 2. So you could go through the whole long process of trying to find the square root of this, just like we did right at the start, but it's going to be very similar to 3 plus 2 root 2. Let's try out, so 1 minus root 2 squared. That's going to work out because we'll get 1 plus 2 minus 2 root 2. Okay, brilliant. So I can just replace it in brackets by 3 minus 2 root 2. Which will give me, first of all, root 2. Oh, sorry. Yeah, no, I've just made a mistake. I've just realized, hopefully you realized as well. Sorry, that there should actually be 1 minus root 2. I forgot to convert it back. So square root of 3 minus 2 root 2 is 1 minus root 2. That looks strange. Okay, so plus root 6 minus root 12 over 2, or root 2 minus root 6 plus root 12. Okay, those are 4 solutions. Really nice question. Involved, of course, solving a quartic, but using a lot of content of first year A-level maths, to be fair. Of course, the challenger bits, maybe even the first part could be challenging if you don't spot to just try some things out. This bit here, realizing that you can write it as x plus a times x plus b, etc. But even if you get stuck with that, you can then still step in and take it over from here, which of course is again involved because you have to somehow combine these to get the equation here. Solve what is actually it's the power of 6, but we can turn it into a cubic. We've solved for s squared, get those solutions. Work out p and q from s squared equals 2, get our quintic now as the product of 2 quadratics, use the quadratic formula, and find these 4 solutions. Very well done.